I'm Neil Patwari. This is ESE 471. This segment I'm going to talk about a short guide to frequency transforms. I'm going to talk about which transforms you might see and where you might use them. So to get to that, I'm going to first have to define periodic and aperiodic. So I'll start with the discrete time signal. A discrete time signal x of n is periodic if x of n is equal to x of n plus n0 for some integer n0 for all values of little n. And the smallest n0 that's positive is the period. Any signal that is not periodic is aperiodic. Okay, and the same would apply for continuous time. So a continuous time signal x of t is periodic if x of t is equal to x of t plus capital T0 for some capital T0 greater than 0 for all t. The smallest such T0 greater than 0 is the period. Okay, so we've defined periodic for continuous time and discrete time. So what we're going to do is we're going to talk about the transforms for these two cases. So when we have a periodic continuous time signal, this is where we have to apply the Fourier series. When we have an aperiodic continuous time, this is where we get to our very familiar Fourier transform. Personally, I learned the Laplace transform first, but if you're more familiar with the Fourier transform, that's the one that's important to know for communication systems, and we will largely not talk about Laplace transform. In the discrete time case, we could have periodic signals, and we'll talk about the discrete Fourier transform, which is called the DTFT. We also have the fast Fourier transform, or the FFT, which is used to speed up computation of the DTFT. Finally, we have for aperiodic discrete time signals, we have the Z transform, and the discrete time Fourier transform is abbreviated DTFT. The names are not necessarily the easiest to remember where they go in this chart, but this is where they go. We're going to use this discrete time Fourier transform in the case of OFDM, orthogonal frequency division multiplexing, because it is easy to compute. It is easy for a receiver and a transmitter to compute the Fourier transform when we can get something that is in this form. Now, generally speaking, periodic signals are not what we see in communication signals. Okay, and the simple reason is that, well, if you're sending the same thing over and over again, the same bits, the same data, the same signal, then it's not a very useful communication system. Once you've gotten it once, you don't need to hear it again. So we typically don't see periodic signals in communication systems, except that OFDM will make some signal modifications to kind of approximate a periodic signal, just so that it's easier to compute. And the main communication systems other than that we'll cover are in the aperiodic continuous time world. And thus we'll be ending up using the Fourier transform quite a bit. And we'll be talking about frequency domain, because that is how our radio spectrum is divided up by the US FCC. And in fact, they'll talk about frequency as hertz. So instead of a mega, we'll often talk about frequency. And so just remember that a mega is equal to 2 pi f. I'm not going to go into detail about how to compute each one of these Fourier transforms. That's up to you to go up and look if you need them. But I will paste in a little chart in case it's helpful. I have some more formulas for the Fourier transform, for the DTFT and the DFT. Those are in your notes if you need to refer to them.